Okay, let us finish with kind of a look forward towards how to go from what we have now to the actual universal machine learning tuning algorithm. So let us repeat the goal that we stated at the beginning of the lecture, and that was to develop the methods that are universal, scalable, and not device specific. So if we just quickly compare the sort of the traditional programming, how we defined it at the beginning with this AI or machine learning view on programming, we have sort of interesting comparison. So far, definitely on a smaller devices, these deterministic, just standard tuning algorithms can perform super well. And even with the AI on a double quantum dot, beating experienced human tuner or a fixed program is still a kind of neck to neck challenge, even though we have some really great examples in the field where in a specific test, the machine learning was a little faster. There is this long view challenge that comes from a fact that if you want to scale up to many qubits, for example, or if you just want to have your operation faster and faster, there are some limitations to how sustainable this traditional programming can be. Machine learning has the great potential, but at the same time, the current algorithms face some challenges. We can see great speed, great generalization. Scalability sometimes can also be an advantage because, for example, here we were just having a very small network that was basically scanning your measurement data on a just on a very small subset and so on. But still, we have some challenges in how to get the fidelities really high. But this is something that the field is super actively working towards nowadays. Just to give some examples, there is a whole zoo of machine learning methods that people are using nowadays. We were talking about using deep convolutional networks in this lecture. This publication here is just another example from another group where they developed just measuring a sort of ray to your closest transition, so you don't even have to measure a square, and then you save a lot of data. People are also using reinforcement learning, where the algorithm tells you themselves what the next step should be without you having to implement it like we did in this simple example. And one can also use a generative model to find the best places to measure. So there is a lot of progress right now in the field. Also on a timeline slide, I had a lot of citations with a lot of exciting papers that you can look up and enjoy if you want to look some more into this. If we want to formulate the goals of what we need to achieve for this field to truly succeed for the next generation of quantum devices, there are some interesting points that we can address. One is direct in situ control. Doing a clumsy thing that we read out the device, everything goes out, and then we have on a Windows computer next to your setup a pre-trained neural network that we apply, and then we have to down propagate that decision all the way down to the device. That's not super practical. So programming the neural network, the trained neural networks directly on a FPGA and directions like that are very interesting, and it's also something that is slowly happening in the field now. Generally, just going for more sophisticated algorithms. In a computer science, you can now talk to the AI and having a really great experience or generate works of art. So really going to this really large scale, heavy, super generalized algorithms, I think it can help us a lot. Another aspect is a quantum machine learning when you do machine learning not on a classical data, but directly on the chip, on a quantum state that you have. So you can directly adjust sort of in a quantum subspace that you're in without necessarily doing readout. That's another sort of emerging field that is very exciting. And the final thing that we need are the sort of standardized benchmarks and standardized databases. Right now, we collect our data to the best generality we can. We determine some fidelity and then we report it in the publication. Ideally, the field would look like that we have a 6 standardized data sets. Similarly, you have MNIST or CIFAR in machine learning, and you just benchmark your new algorithm on the standardized data set. So this is the end of my presentation. I want to just finish with telling you that there is a lot of machine learning sources out there, but connecting this computer science to the actual device can be really tricky. But at the same time, there is so many great resources that let you do your first neural network in just a few lines of code. So if you are thinking about how to get started in this field, the best thing is just to do hands-on on your own device. You can think about if there is just like a simple tiny tuning step that you could in principle replace with machine learning, with this sort of input label type of task. And if that's a yes, then you can just try to implement the simple neural network for yourself and just learn this by doing. And after you succeeded at that, there is a very short path towards implementing some more sophisticated algorithms and actually contributing to this super exciting and emerging field. Thank you for listening.